discuss how we solve more complicated sequence problems, claiming that they relate to the complicated Galilean theory of free-fall motion. And so we imagine that we have this sequence 2, 4, 7, 11, 16. Now, I call delta 1 the change in the first two quantities. Delta 2 is the change in the next two quantities, and so on, so that I get a sequence of deltas, and the sequence that they form is 2, 3, 4, 5, and so on. Now I call delta delta the change in the change for these quantities. And in this case, it's equal to 1. So if we could find a closed form formula, namely this one, in the case of arithmetic sequences, maybe we can find one for these ones for which delta is not constant, but delta delta is constant. Now, the first, like what kind of a formula would it be, or how do we find it? We could guess, right? We could, we would not expect it to be linear though, right? Like we know that the fact that everything changes by a constant 2 here is kind of what makes this work. This thing changes in a sort of funnier way, so you would not expect the formula to be as simple as this. You would expect it to be a next level of complication. And how do we sort of figure out what that next level of complication is? Well, this formula is, so to speak, linear in n, right? Because it's basically of the form y equals mx plus b, where, or let me say y equals mn plus b. And that's because it's got a first power, right? That's really what makes this linear. If we had a quadratic equation, we would say something like x squared. That's quadratic. That's an example of a quadratic equation. Well, here the n is to the first power, so that makes this linear. And we might think that the next more complicated form of an equation is a quadratic equation. So maybe we guess that this constant delta delta has a quadratic solution. So let's suppose that it does, right? If we suppose that it does, then that gives us a little bit of something to work with, and then we'll figure out exactly which one it is. So if we guess that it's quadratic, then maybe I would guess that the formula is a sub n equals 2n squared. After all, that will get the first term right. If you plug in 1 to get a sub 1, you'll get 2, right? You plug in, 2 times 1 squared is 2. So it gets the first term right, but does it get the second term right? If I plug in 2, I'll get 2 times 2 squared, which is 8, whereas what I wanted was 4. So no, it does not get the second term right, and this cannot be the correct formula. Now, we could keep guessing, but it's probably better just to say, let's call the formula an squared plus bn plus c, and if the sequence is described by this quadratic equation, we want to know what is a, b, and c. Well, what do we know about a, b, and c? We know that if you plugged into this formula, if you plug 1 into the formula, it should tell you the first term, which is 2. So if you plug in 1, you should get out 2, which produces this equation here. And we could simplify that equation and get this equation down here. And we could do it all over again by plugging in 2 to get a sub 2. A sub 2, we know, should be 4. So if I plug in 2, I set it equal to 4. That gets me another equation. And then I do it again by plugging in 3, and I get this system of 3 equations with 3 unknowns. Now, you could take a class in linear algebra to learn how to solve a system of 3 equations with 3 unknowns, but that's not really our focus, and so I'm going to use SymPy's equation solver to tell me quickly what that value is. So I have here exactly that, right? I have this expression a plus b plus c set equal to 2, and I've saved that equation. I've done it again with each of the other equations, And then I have put all three equations into a list, right? This is kind of like grouping the three equations together. This is the syntax for how you do that in Python. And I've thrown that list of equations, that group of equations, into the solver, and then I've had SymPy print it. So pretty please pretty print it. And it tells me the coefficients. It tells me that A is equal to a half, B is equal to a half, C is equal to a half. So with that solution in mind, let's go back and check that it's actually getting us the correct values. If we look at the formula A sub n is equal to this formula in n, then we plug in 1, and if you calculate it, it comes out to 2, the correct answer. If you plug in 2, it comes out to 4, again, the correct answer. It looks like this method has worked. And so in this sense, we could say that Galileo's theory of physics predicts that objects under free fall should move quadratically, right? The formula for their motion should be a quadratic formula. And in fact, if we actually do empirical investigation, we confirm that that's true. And we can even say what the acceleration, right, the change in the change, is for this sequence of numbers. And if you measure it carefully enough, you get that the acceleration is 10 meters per second. And if you release something with no initial velocity, it is governed by this equation, where h is the initial height and t is the time, and this tells you the height. So I'm describing an object falling under free fall and getting closer and closer to the ground. That's why it's, you know, behaving with a minus 4.9 t squared. As time goes on, it goes down, starting from an initial, one would typically take a positive initial height. Now, if it has initial velocity, you just give it this extra term. So this is the formula that describes the motion with some initial velocity. And this is the important formula, right? This is the formula for free fall motion with some initial height and velocity. And this really gives us something to measure and predict. And we can actually use this to predict the motion of objects, and everything works out correctly.